having more than 10, for example, micrometers, with more larger silicon installed. And we don't see the effect of grain boundaries on the mechanical properties, for example. But anyhow, now the problem will happen that because of the fact that the depth of indentation limits to just some nanometers, this process is very sensitive to the topography of our surface. And it was the reason that we took a special care on the surface preparation of our alloys. After verifying mechanical polishing, we did electro-polish our surface, and finally the roughness of our surface was less than 1 nanometer in average. Here you can find a list of materials I used for my tests. I used 2 groups of materials with different concentrations of chromium and titanium.
There's a fire starting in my heart, reaching a fever pitch and it's bringing me out the dark. Finally, I can see you crystal clear. Go ahead and sell me out and I'll lay your ship bare. See, I'll leave with every piece of you. Don't underestimate the things that I will do. There's a fire starting in my heart, reaching a fever pitch and it's bringing me out the dark. The scars of your love remind me of us. They keep me thinking that we almost had it all. The scars of your love, they leave me breathless. I can't help feeling we could have had it all. You have my heart inside, and you played it to the beat. Baby, I have no story to be told, but I've heard one on you, and I'm gonna make your head blow.
Alloy, where the grain size is quite smaller than in the 6000 alloy. And after 6 ARB cycles, you can see here the second order once again, you can see that the 5000 alloy is really, really fine, and the 6000 alloy is a little bit bigger, but you can clearly see the interface and the grain structure. What was also coming out now is that for higher number of ARB cycles, the structure at the interfaces is becoming more and more wavy for increasing number of ARB cycles. And we found that at these positions where you have such waves, you find shear bands in the 5000 alloys forming. And this was also already found by Fadi et al. And is due to the shear you receive at the interfaces, where the one material wants to flow and the other one is then pulling on the other, and therefore these shear bands form at higher deformation rate when the difference in strength is increasing. This is more obvious now when I show you the local mechanical properties. On the next slide, you can see it here. The 5000 alloy is in the middle here. This is going to the middle of the sheet. The 6000 at the outside, and you see here the nano indentation array going across this, and you can see in the hardness profile, the 6000 alloy is a little bit smaller than the 5000 alloy in hardness, and for a higher number of layers. 4 cycles, you can see that the jump in hardness is increasing for these 2 materials. And always go, the lower hardness is the 6000 alloy, the higher hardness is the 5000 alloy. For 6 ARB cycles, you can see here also these clear jumps. And what was obvious now is that the strength of the 6000 alloy is only increasing up to 4 cycles, is saturating after
more information until the crack was formed. And when you take the color code into account, you can see that the other fine grained sheets show a much better deforming behavior than the cold road state. Yeah, and all in all, we can see we have very nice properties of our fine-grained materials, but there is one big drawback, and this is the restricted sheet size of our laboratories sheets until now, and therefore there's a certain need to upscale them, and of course there arises the question whether the mechanical properties which we claim to be very nice can be maintained. And
this is your life tonight, everything's gonna be alright. This is your life tonight, everything's gonna be alright. This is your life tonight, everything's gonna be alright. This is your life tonight, everything's gonna be alright. This is your life tonight, everything's gonna be alright. Everything's gonna be alright. This is your life, everything's gonna be alright. This is your life, everything's gonna be. 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 This is your life, tonight, everything's gonna be alright. That's all right. Thank you.
MSE party as much as I did. A lot of tired faces. But anyway, we start with the plenary session this morning. My name is Christoph Lyons. I'm a university professor and director of the Institute of Material Science at the Technische Universität Dresden, which is the technical University of Technology in Dresden. I'm also with the Fraunhofer Institute in Dresden. So it's my great pleasure to introduce our plenary speaker this morning, Professor Christopher Schuh. He is the department head and also professor of histology in the Department of Material Material Science and Engineering at the Massachusetts Institute of Technology in Cambridge, Massachusetts, USA. He has a bachelor's degree. Are of course very common. And if you're working on crystalline materials, there's an entire family of paradigms that you can chain together to model deformation processes from the scale of the electrons all the way to the macro scale by simulating through DFT or molecular dynamics or dislocation dynamics up to finite element models. The idea is that to understand deformation behavior at the macro scale, you can chain together understandings from all the scales below. And this is a vision that has come together over 15 or 20 years in the domain of crystals. What I'm here to tell you today is that in the domain of amorphous materials, that paradigm...
Thank you very much for the introduction. I'm not going to read the long title of my presentation again due to the short time I have, but I'm going to talk about also ductile iron, and I'm very happy that some of you are brave enough to understand here what I'm going to tell you. So when we start with a short outline of what I'm going to tell you, it's, you can see it here. I'm starting with an introduction where I will make you all familiar with some fundamental features of tempered or auxeric ductile iron, ADI. Then I'm going to show you some results that we got from a project where we characterized a number of different alloys for these as ADI. And I'm going to talk about the influence of microstructural deviation. I'm now open for questions.
Thank you very much. The talk is open for one short question.
We have
the cooling rate. The question was how we control the cooling rate.
So we have a equipment for dilatometer measurement. So we have small specimens that are like a match maybe, and the cooling rate is controlled by this equipment. So we can do it by helium or nitrogen. We heat up and then cool down by giving the gas to the equipment.
Thank you very much again. And we will shift to the next speaker. Okay, the next speaker is Mr. Zachariaev, and he will talk about the properties and structure of low-carbon steel traded by combination of severe plastic deformation and conventional deformation. We're very interested in your talk.
Good afternoon. Thank you very much for introducing. The topic of my report is properties and structure of carbon steel treated by combination of SPD and conventional deformation. Short outline of my presentation. Severe plastic deformation of metals are recognized method for formation of structure and properties of ultrafine grained materials. SPD implies deformation under the effect of a number of forces or those moments. Researchers accumulated a large amount of data concerning the collective effect of shear strength and pressure at the process of structure formation. Combination of these two factors gives an opportunity to perform cold plastic deformation with accumulation of the large strain debris. A new class of materials is produced that demonstrates high level of strength and conserved plasticity. But the used schemes do not permit the production of materials in the quantity sufficient for wide commercial application. So, the aim of present report is analysis of the structure and the properties of low carbon steel after hot rolling with further cold drawing. The most popular scheme of hot or warm SPD is isothermal all-round forging used to production of ingots of titanium alloys, and rolling with shear applied to production of steel ingots. Rolling with shear is characterized by variable shear deformation in the process of metal formation within the roller passes. Plastic deformation of metals is accomplished at least twice with partial reduction not less than 10%. A characteristic of scheme is that rolling in ancient passes is occurred with grooves displaced along the axis of rolls at the distance of 20% of grooves width. So there is a 3D model. A special interest is demonstrated to the schemes of continuous SPD, providing production of the materials with modified strength plasticity ratio in the quantity acceptable for commercial application. Undoubtedly, compared to cold SPD, hot SPD yields much larger grain in the deformed alloys, but such deformation allows formation of ultrafine, homogeneous, isotropic, and uniaxial grains, with dominating of high angle boundaries and low density of dislocations in the pulp. The first effect of such structure formation is availability to product steels with high level of strength and plasticity at the same time. The second effect is formation of structure without anisotropy with respect to the deformation axis. The result is high level of plasticity resource in the case of succeeding processing. As investigated material was low carbon constructional steel. We use such deformation method as traditional hot rolling, ST technology, and hot rolling with shear, RS technology, both combined with further cold drawing. The material structure after rolling with shear is characterized by structure isotropy in transversal and longitudinal directions. The metal rolling with shear material provides uniaxial grains without size dispersion as distinct from ST technology. And the BSD data of error space and grain boundaries maps was obtained for hot rolled material. It is seen that after hot rolling with shear, the structure of low carbon steel is more fine and uniform as in comparison with standard hot rolling. This is the cause of peculiarity of deformation scheme. To determine the value of grain boundaries misorientation distribution, BSD data was applied. The amount of high angle and low angle boundaries in low carbon steel obtained by different techniques are illustrated. It is well seen that the standard deformation scheme results in formation of a great number of low angular boundaries, and rolling the shear forms mostly high angle boundaries. For detailed analysis of scene structure, the team investigation was done. The risk magnification is equal to 20,000 at accumulated plastic strain 2.7. The triple junction of ferrite grains are illustrated. The triple junction of ferrite are illustrated. After rolling the shear, the average diameter of ferrite colonies is half the average diameter of ferrite colonies after standard rolling. Besides, material processed by RS technology has dislocation-free ferrite grains and thicker grain boundary. The traces of dislocation flow toward grain boundary are seen. These data bear evidence of intensified defect motion in the course of deformation by RS technology. Active motion of defect toward grain boundaries results in thickened grain boundary. High mobility of dislocations is determined by the fact that dislocation with the screw component, dominating material after RS technology, which can change their slip plane at the deformation. In the case of this is the case of dominating high-angle boundaries at rolling with shear process. Properties. The experiments demonstrate that the strength characteristic of metal after RS and ST technology are comparable. At the same time, plastic characteristics have some specific features, as you can see. Technological plasticity of metal under RS technology is 40% higher than that after traditional rolling. In contrast to ST technology, there is alternate decreasing, increasing of grain size with strain growth. Nonlinear grain size characteristic at rolling with shear combined with fault drawing are illustrated. You can see nonlinear grain size evolution. Also, it was conducted a BSD analysis, so a BSD maps of microstructure and grain boundaries at rolling with shear combined with further fault drawing are presented. The fractograms of samples after RSD demonstrate lower amount of pores at that for STD material. STD material, it means standard treatment and physical drawing. RSD material, it means rolling with shear and physical drawing. There are some specific features in evolution of strength and plasticity. When the deformation degree increases, the process of strengthening and loss of plasticity in the case of traditional rolling with succeeding drawing occurs more intensively, as you can see, traditional. And with primarily RS processing, the strengthening is not so intensive, but at the limit value of accumulated strain, the yield stress is equal to 1030 MPa, as distinct from standard technology with 900 MPa. We should note that RS technology provides 25% higher ductility at the same magnitude of plastic characteristic. Classical behavior is demonstrated by evolution of density and microhardness of the STD material. With the increase of deformation degree, microhardness increase, microhardness increase and densities decrease. This is the classical behavior. And some increase in the density at the deformation degree equals 0.4 is determined by the application of softening annealing due to impossible additional deformation. The decreasing of microhardness at the final stage is caused by accumulated porosity and microcracks. Absolutely different characteristics are registered at ISD application. The behavior of density and the microhardness is changed. In the case that density drops with increase in microhardness, another behavior is observed here. At the first stage, microhardness and density are both decrease, but at the second stage, microhardness and density are both increase, as you can see. The behavior of the material can be explained by the effect of IDM, induced defect motion, intensified defect motion, In the case of deformation with the shear, under SPD, the material accumulates a lot of energy that dissipates in the rate of generation of dislocations with the screw component and increase the mobility. Thus, at the further deformation, Annihilation of dislocations take place due to two possible processes. The first process is close to Bausch-Schwinger's effect. With respect to the mechanism, because of sign of the load application is changed and metal flows in the direction normal to the last deformation stroke. The second process is active flow process of vacancies and dislocations toward grain boundaries because of IDM. So, unusual change in the physical and mechanical properties is based on specific mechanism of deformation. And I should conclude that an example of low carbon steel deformed by rolling with shear, it was shown that hot severe plastic deformation leads to formation of structure with ultrafine homogeneous isotropic and uniaxial grains. There are dominating hierarchical boundaries and low density of dislocations in the bulk of the grains. The features of the structure are inherited after the succeeding deformation. The last one, it was shown that the use of rolling with shear combined with cold drawing allows obtaining the wire of small cross-section without intermediate anneal due to high plasticity resource. It should be noted that the last one allows to achieve great economy effect. Acknowledgements, and how wonderful that we have met with the paradox. Now we have some hope of making progress near its port. Thank you for your attention.
Thank you very much. And again, time for a short question. Don't see any questions. Then thanks once again.
Thank you.
And I would ask the next speaker. Mr. Kusekin from the Belgorod University in Russia. He will talk about the effect of cold rolling on microstructure and tensile properties of a high manganese steel with a twinning-induced plasticity effect. We are interested in the talk, and you have the word.
My talk, I first present the process and the process validation, and then we will have a quick look about the sintering behavior on model material, which is the first topic for the panel we conclude. So to get material with improved properties, one way is to have a microstructure control, either by nanostructuration or texturation. So we have chosen the powder metallurgy route because you can sinter virtually all materials and you can have millimeter to nanometric powders. So after choosing the powder, generally you have a compaction step followed by a sintering step and you get your final product. So the process I'm going to present focus on original way of compacting and sintering. Advanced process already exists, but there is a need to go further. So the approach was to combine the most advanced flash sintering process because we have shorter processing time and lower sintering temperature compared to
dependence on a single hormone parameter. This dependence can be seen in flow curves when you have a change from a single peak behavior to a multiple peak behavior. But much more important is that we have this very nice steady-state flow stress and also a steady-state grain size, which can be adjusted by the change of the strain rate or have been evaluated, and it has been shown there that you can decompose the flow stress in this change into two parts. The first one is an instantaneous change until the strength of the flow stress here, which is just due to the change of the deformation parameters. And then you have the second part, which is continuous change to this new steady state. And because there's only left to change change the microstructure to this new deformation parameters, this is the important variable that has to be changed. So here we have our grain size sensitivity of the flow stress, and these grain size sensitivities have been evaluated. As you can see here, you get this nice plot of it. When you plot it against the grain size change, which is an equation of this kind, and the most important thing of it is that you get the slope of -2, because then you have the possibility to transform this equation to this kind. And here you have, for the first time, a physical-based relation, or a physical relationship between the flow stress and the steady-state grain size on the basis of this grain size sensitivity. And another fact that is pretty nice here is that there is a similar relationship for the flow stress and the subgrain size, so we can correlate the subgrain size and the grain size as well on this physical basis. So now I'd like to show you how this concept works. At first, we have, as usually, a generation of duplications. These duplications are then arranged into a cell network, and the cell walls will then, with continuing deformation, condense and turn into subboundaries. And here's this critical condition, as I told you. These subboundaries become mobile, and so they can adjust. And as you can see here, we have this unbalanced high-angle grain boundary, or unbalanced due to the subboundaries on the left and on the right. So what will happen is that this grain boundary will start to bulge to adjust to get balanced in the triple junctions there. And in the meantime, you have new dislocations generated, which will again arrange into a new sub-boundary network.
Texture component has high R value with small anisotropy. The aim of this work is to improve the R value of solution treated 6000 series aluminum alloy by controlling liquidization texture through symmetric rolling and subsequent asymmetric rolling like this. And we obtain the 111 texture evolution and
let me work on that one. And stacking convergence is proportional to temperature and compositions. And there are a lot of work on this in the 20-inch plasticity steel because it is thought about as an automotive steel, and that's why people are too much involved into that, and they talk about that if it is lower than 16 millijoules, they can form some external martensite. If it is a little larger than that, then there is any effect in that. Of course, these all the 16 or 25 this is based on some kind of ab initio calculations, and we really don't know how much this is valid because in practical sense, this has no meaning. Only we bother about whether.
But what I got here is what I designed, the structure is, this is a magnetic sensor here. What I put in here is a piezoelectric radiometer. I put two piezoelectric sensors in here, which I can cancel each other out within one magnetic sensor. So I basically, you can see here, there's two piezoelectric sensors, one there, and I have an extra kapton layer, an interdigital electrode layer. So I have one piezo sensor 1 and piezo sensor 2, but magnetic sensor 1. So I can measure then the charge output of either one of these two piezoelectric layers in response to a magnetic signal along the long axis. And you can see these here, right here, in terms of red and blue individual sensors. I subtract them. No, I add them because they're out of phase. And you can see the black line. The noise signal is gone. That's on a shaker, I put it. So I shake it, and I get two signals out from the vibration. I add the signals together, the vibration and noise is gone. magnetoelectrical potential is doubled. So I can double the gain while I kick out the acoustical noise, or acoustical signal. Now, if I'm smart, since I added it, and I got the magnetic signal, if I subtracted it, I can get rid of the magnetic signal, and I can get the acoustical signal. I've got two signals sitting right here. Now, this shows the power spectral density. This is frequency, this is frequency versus time, this is amplitude of the noise, sensor A and sensor B.
Microscopy and Kikuchi analysis, perhaps it was Hunter who did this as well. They used to analyze it by taking Kikuchi lines, areas, and putting them onto a sphere, right, and then comparing what they saw with what they looked on the sphere. And this is quite the way to do it, because in fact, what comes out of here is a spherical set of Kikuchi patterns. And what you see, in fact, is the projection of a sphere, right, onto a plane. And this is this economic projection. And what happens is that when you have a sample here, you can imagine a reference, and a reference sample, which is undistorted, will any vector R, we'll call this a vector R, will go to a point P. However, if you then deform this area here, the vector R will go to R prime, right, which leads into P prime, and the shift from P to P prime, we call these Q. These are the little yellow line, the yellow arrows, the shifts, right? And you can use the geometry of economic projections to show this relation. This is the basic relation of high resolution EBSD. In other words, that the R plus Q, R prime, right, is related to the pattern center coordinate, Z coordinate. F is the deformation gradient tensor, and R. By this relation, and of course the K is the normal to the phosphor screen, right? And you can see immediately that this is not a linear relation between F and Q. So what you want to do is to take the measured values of these quantities and then calculate F using, in fact, it's non-linear optimization techniques for what is a certain number of these different shifts. Instead of having just one shift, you can take another area here, another shift, and you have a whole set of different shifts. And therefore, you cross-correlate what we call regions of interest between the reference and the deformed states, get a whole set of different Q values, and solve this to obtain F. So this is the basic principle. Now, I said that Winkelmann had shown how to get simulations, and this is an example. This is a pattern of a germanium crystal, and this is the true experimental pattern. This is the intensity distribution. And if you do a multi-beam dynamical simulation, then this is the simulated pattern. You can see that this is in pretty good agreement with this. And now we can use these patterns, right, to work out the way that crystal structure, lattice orientation, and sample geometry, right, will affect these patterns. The middle one, right, is a type of Bradshaw type simulation that some of us have used in the past, but now we've abandoned for the last 2 or 3 years. So we will use these type of simulation to find out the influence of all these different parameters. Now, this is all, the theory is all very fine. We have to look at some of the practical problems. And the first is what we call lens distortion. A beam comes in, hits a sample, the electrons are backscattered, and then they go on till they go through the camera. They go through the phosphor screen, right, transform into photons, and then onto the camera. And this is a more detailed vision of what, due to Austin Dave, and what happens is that they go through coating of the phosphor screen, the particles, the glass, then the lead glass window, the lens, and they are on the CCD chip. And it is always worth remembering that out of 100 electrons backscattered out of here, only one is captured, the influence of one is captured on your CCD camera. 99% are lost on the way. Second point is that when the one that survives gets through here, in fact, it is slightly, its trajectory is slightly deformed by your lens system. And this, in fact, is, this was actually they who pointed this out to us a couple of years ago, and so we worked on how to correct for this. And in fact, the correction is relatively simple. Basically, what you do is you take some kind of checkerboard pattern, right? You take away the phosphor screen, and you look at the checkerboard pattern through your camera system, and look at the image. And the image, in fact, of this pattern is distorted. So this is going to be very right. This is the checkerboard pattern. This, in fact, is what your CCD camera sees. And if you look on here, then you can see this is the way that some lines, and you can see that it's rotated, it's barreled, these are not major problems. They have no influence on standard EBSD, but they have influence on measuring small shifts in the pattern. And the question then, what you can do in fact is you have to, if you like, go back to this. You have to determine from this pattern the distortion parameters, and this is what has been done by image analysis people for 20 years. Right? And you calculate the distortion parameters for your particular configuration, and then for each pixel, you will then remap or undistort the EBSD. So this is what you do. You have to initially, you have to undistort your EBSD to correct for lens distortion. And in fact, to our knowledge, this is only people have only started doing this about a few months ago. Then the second problem is what we call the problem of orientation gradients. Is that if you have a perfect single crystal, then you don't have any orientation gradients. But if you're looking at which is more interesting samples, which have got dislocations and subboundaries and things like that, they have orientation gradients. And they are typically a few degrees. Now then, in the initial work, when people compared the pattern shifts on the sample compared with the reference, initially people thought that any orientation difference between the reference and your current sample area had no influence. And this was work that Claire did on looking at the influence of what happens when the reference EBSP is misoriented from the current EBSP. And using simulated patterns, you can use a numerically simulated pattern, and so you know all the exact orientation, the strain, the shapes, you know everything. You could compare it then with what you would expect, what your sort of cross-correlation method, partnership method would give. And this, in fact, shows that if you have a rotation angle, here we're looking at the error which is induced by rotations from the between the reference and the current pattern. And this is 0 to 5 degrees, and the strain error is up to, this is 10 to the minus 3, right? So that you have a rotation of about 3 degrees, right, between the two reference, between the reference and the current pattern, and you have an error of the order 10 to the minus 3. And you want to have measurements to 10 to the minus 4. And therefore, you have a major problem. Right? And this, in fact, and why is this error? Because the shifts are distorted by the rotations. The rotations change what we call the cross-correlation peak, for those of you who know about cross-correlation, right? And the shifts, in fact, are deformed by this lattice rotation. And so this is could be a major problem. Right? And in fact, solution is being proposed. The solution is as follows. For your reference, this is your reference pattern, this is, let's say, your current pattern. Then between the two of them, you know what the rotation is, because this is simple 2D half transform. You know, it's 3 degrees around this and this, whatever. Right? So you know the misorientation between here and here. And what you can do then is to rotate the reference by this known misorientation. So you apply a rotation on this pattern. In other words, you remap the entire pattern. Remember, you remapped it first for edge distortion. You remap it second now to correct for the rotation. Right? And this is the rotated reference. And then you compare the rotated reference to the current pattern using cross correlation. And this will give you misorientations and lattice strains to a really high degree of accuracy. And this, in fact, was published earlier this year, so it's quite a new development. And we call this the rotated reference technique. And this is an example. Here we're looking at the shift errors, the errors on these little yellow arrows. All right? This is the standard method without RRT, the shift errors of the order 10 to the minus 3, 10 to the minus 4 radians. Remembering that you are measuring things of this order. Little arrows are of this order, right? If you apply the rotated reference correction, right, then your shift errors are about 10 to the minus 5 or 6 or something like that, right? So they are way off. So we believe we have solved this problem. And when you do this, right, then you can measure local elastic strains, disorientation, and you get physically realistic values. If you don't do that, you get abnormal values. I've just seen a paper in Scripter, where's the author, right? Scripter, which says that somebody published some results showing that they got terrible, physically unrealistic values. That's because they hadn't done the corrections.
It's not my paper.
Oh, it's not yours. So this is an example, right? This is a grain. We have this. We deformed about 10% some kind of steel, low kind IF steel, I think. And here we're measuring von Mises stresses. Now these are the errors, if you like, right? Angular errors, right? And these are the stresses that you would calculate from the strains that you measure. Right? And here you can see large values, which are the order of 600 megapascal, but the material has a flow stress of about 300 or so, megapascals. On the other hand, when you apply the RRT method, then this is what the stresses that you find here in the grain, which are typically for less than 400, the average is about 200 or so, which is what you would expect. So, now the other problem is the pattern center. We said that initially, when I showed you the beam coming in, hitting a sample, it's a pattern center. And if you remember, the formula that gives the relation between Q and F involves the pattern center. Now, the absolute value turns out to be not very important, but relative shifts in the pattern center, right, can be very awkward. The relative shifts occur when you're doing beam shifting to make a marker. As you shift the beam, then your pattern center shifts relative to the original point. And this was work done by Willett a few years ago, and he measured for variations in the pattern center, this is the X value, right, and showed the errors, or what we call phantom displacement gradient components, right, due to pattern center variations. Remember, you have about 1,000 pixels, so 0.05 is a few pixels, it's 5 pixels, right? You have this amount of error in your pattern shift in your pattern center, then you have an error of about 10 to the minus 2, which is gigantic. Right? So you have to avoid these shifts, in particular relative shifts in the pattern center during beam shifting. And this you can do realized after this work, you can do this by geometrical considerations. So, therefore, we have to write a geometrical compensation for the instance. And so I will just give you now a few examples of what you can do and how to correct for things. And the first is looking at low angle boundaries. And here we're looking at nickel-based superalloy single crystal. And of course it's a single crystal, so by standard EMSD you get nothing but the orientation. This is what it is, what you see in the oil angle. And if you, for the same data set, for every pixel, you apply high resolution EMSD analysis, then this is the image you get. This is the map you get of orientations. And the oil angles, if you look here, they go from 1.703, right? They're a small variation, 0.2, 0.3 degrees, right? So it's a very small scale, right? Right? So here we're looking at variations of, tenths of degrees. And this is the misorientation distribution, and the average misorientation is about 0.1 degree. Right? So these are the low angle boundaries that you are seeing, which are typically around 0.1 degree, which is the accuracy of 3 TEM or better. Recalling, of course, that standard EBSD gives you an angular accuracy of about 0.5 degrees. So, of course, with standard EBSD, you would see nothing at all. So the first thing you can do then is to measure low angle boundaries, or boundaries with much higher precision than anything before. Second is looking at just pure elastic strains without any plastic deformation for the moment. And this is work that was done by Willett a few years ago. He took a silicon single crystal, right, and bent it, or 4-point bending at a microscope. And now, of course, when you bend a crystal, then one surface is in compression, the other surface is in tension, the center is 0, so you have a reference which is right in the middle. And then using this technique, you can scan it. What he did at the time, in fact, was a stage scan, because we knew that beam scans at the time, they were dangerous, right? At the time, we didn't have the correction for the beam scan, but we did the stage scan, so we went through here, right? This is distance, and measured the strains, right? And these are different strains, Y, X, Z, right, and all the rest of them. So these are the strain measurements. Of course, the center should be 0, which it was, right? And since it's a simple beam, right, so it's a bit anisotropic, you can calculate the exact solution. You know what they are? And the exact solutions, in fact, are the straight lines for these different strain components. You can see that it's getting very good agreement. So within about this area, this is about 10 to the minus 4, or 2 times 10 to the minus 4. So it is true. You can measure elastic strains to this type of accuracy using high angular resolution EBSD. Now, if you can do this, you can go back to what Truce did and looked at silicon germanium epitaxial plots. And this is a map of elastic strains. Here is just showing the normal strain component. As I think these are areas where it is deposited germanium on silicon, so it increases by lattice distortion the strain. Right? And these are the elastic strain values, right, as measured on this map. And they fit very well with what you can calculate. In fact, it fits so well that now you can estimate the composition from the elastic strain. Since you know that so much germanium will give you rise to so much elastic strain, if you know the elastic strain, you can say, well, I've got so much germanium. Right? So this gives you, if you like, almost chemical composition. Now, what has people been doing? 2 minutes. What people have been doing over the last few years is to look at GNDs. So I will go through this pretty quickly. Basically, you have nice dislocation density. which gives the alpha, which is dislocation density, and a Burgers vector, and tangent line vector, which is equal to this, which are the derivatives of the rotations in space, and in 2 dimensions they are taken from EBSD maps, which means that you only know about 5 of these components. And in fact, for FCC crystals, you have 18 types of dislocations. And so this is undetermined, and you need some kind of additional minimization, and we here do the total dislocation density. And this gives you a map of a cube-oriented nickel crystal, which is plane strain compressed, on a strain of 8.5, and produces misorientation deformation bands along RD. RD is here. So this is a Rodriguez vector orientation map, so you can see you're developing large orientation gradients and transition bands. And the transition bands, right, are accommodated by GNDs. And using this analysis, that I just very briefly described, you can calculate the GND, the local GND density, and this shows the GND density on the same area. And you can then take the average, right, and work out what is the average dislocation of the GNDs. And we were surprised that nobody seems to have done this, but this is very elementary. If you take these, from the GNDs you work out the average dislocation density is about 2 times 10 to the power of 14 square meter. And using the standard relation for flow stress and the square root law, you can work out that the total dislocation density should be about this value, taken out, which is about twice the value of the GNDs. So GNDs in this sample are about half the total dislocation density. And I believe this is a bit higher than usual because it's got a lot of decomposed deformation bands and transition bands. And then finally, right, 2 minutes, right? 1 minute. This is a more recent observation. What I've shown you so far are either pure elastic strains or pure plastic results of plastic strain, which are GNDs, right, but not elastic and plastic, which is more difficult to do. Right. Now this is an example of a stainless steel low stacking bottom in single crystal, and it is scanned across here and in a high resolution EBSD, and we've got strain variations. This is the epsilon 1,1, this is 1,2, 1,3, and rotations R3, R2, R1. And you can see there's a linear defect going across this sample. And this is what you would usually do is you look at these in the sample coordinates, right? What you have. And the linear defect, if you look at the crystal, turns out to be parallel to a 1,1,1 slip plane or a trace. So the question then is, let us look at the elastic strains and rotations in the coordinates of the possible slip systems. So this is the 1,1,1, it's a bar 1,1, right, and it's got 3 possible Burgers vectors, 1 bar 1,0, 1,01, 4,1,1, and this is looking at rotation about R1 about the Burgers vector, about the line vector, rotation about N. And in fact, there's no, if you like, there's extinction, right, for rotation about N, which means, in fact, if you remember about dislocation theory, that these cannot be screw dislocations. And the strongest, right, is for rotation about R1,2,1, which corresponds to the line vector of this one, which means that in fact these should be a linear array of dislocation, edge dislocations with a 1,0,1, this Burgers vector on this slip plane. We believe that this is the first example of dislocation identification using high resolution EBSD. So the conclusions are that high resolution EBSD has a major potential for material science applications, but only if you exercise great care with the sample to screen to camera geometry. In other words, you have to apply lens distortion corrections, orientation gradient corrections, and EC if you can do it. And these are quite extensive numerical corrections that have to get right to the patterns. And if you can do this, you can measure two-dimensional elastic strain components to accuracy of about 10 to the minus 4, which is really very interesting, at scales of about 30 nanometers. And the applications that I've shown you include Randall boundaries, GNDs, elastic distortions, which are a result of very local chemical or physical variations. So I would like to thank you for your kind attention, and I would like to wish all our best wishes to Valentine's family. Thank you. And also I would like to dedicate to Professor Doku. Doku was a professor at Godinin, and he passed away this year. And he was, when I was there, he was a strong proponent of doing very high resolution angular, very high angular resolution measurements. And for those of you who know about grain boundaries, he was the pioneer, or a pioneer, of grain boundary measurements. So, thank you very much.
Is based on the combined effect of high frequency impact of special strikes and ultrasonic oscillation in treated material. The basic portable the basic ultrasonic pinion system UP600 can be used for fatigue improvement of weld as well as ledge surface if necessary. The system is designed for automatic as well as a manual operation. Investigations were performed for welded joints of aluminum alloys 2024. This alloy is considered hard to weld with conventional fusion welding technologies. Due to its high strength and fatigue performance, 2020-43 is one of the most common of high-strength aluminum alloys. This alloy is widely used in aircraft structures, especially for wing and fuselage structures, and the tension where high durability and crack growth resistance is essential. Here you can see basic mechanical properties of base material and welded joints. The beneficial effect of ultrasonic pinning is achieved mainly by relieving of harmful tensile residual stress and inducing compressive residual stresses in the surface layer of metals and alloys, decreasing of stress concentration on weld zones and enhancement of mechanical properties of surface layer of the material. Ultrasonic impact treatment was performed on both sides of fusion welded joints using the UP600. In this view you can see UP treatment face and root respectively. Specimens for fatigue testing were manufactured out of separately welded lens with weld starting and ending on running and run tape. Specimens' appearance and dimension are shown in this video. And specimens were tested using servo-hydraulic testing machine MTS. Excel load was applied according to sinusoidal load time function. The stress ratio was set 0.1 and 0.4, and the oscillation frequency was 5 Hz. Specimens were tested until complete failure. This slide represents the results of ultrasonic impact treatment of weld notch leads to an increase in stabilization of weld notch radius, promotion gradual decrease of stress concentration from weld notch. UP600 is equipped with replaceable striker heads for surface treatment. To determine optimal
project which we have done in collaboration with our European partners. So here you can see the different people who are either present or ex-visitors in our Center for Advanced Hybrid Materials, which, somehow jumped, which is led by Professor Yuri Estrin, whom you all know. And if you look at the faces, we've got a representative from different countries around the world, including Germany, Switzerland, America, Korea, Russia, Ukraine, China, France, and so on. And you might ask me why we have such a stream of the...
Just put it back.
Yeah.